So here we're looking at the mechanism of a carbocation rearrangement in the form of a 1,2 hydride shift. So we have our orange electrophilic hydrogen highlighted. Our pi bond donates its electrons to form a bond to this hydrogen. The bond between H and Br breaks, sending those electrons to bromine. And that gives us our secondary carbocation that is not that stable. Now we will have a hydride shift. It will move from one carbon to the second carbon immediately adjacent. So we would say 1, 2. We only have to count to up to 2. If you have to count more than 2 to move the hydrogen, 1, 2, 1, 2. If you have to count more than 2, then it's not possible. So this hydride shifts with its bonding electrons over to the secondary carbocation. That will leave this carbon with only 3 bonds, as shown here. When a carbon only has 3 bonds, it has a positive charge. So now we have a tertiary carbocation. The minor product is formed from the secondary carbocation, with bromine adding to the secondary carbon. The major product is formed from bromide adding to the tertiary carbocation. Here we have the mechanism for a carbocation rearrangement with a 1,2 methyl shift. Again, if you have to count to more than 2, 1, 2, then you cannot make the shift. So this starts out in the regular way. The pi electrons are donated to make a bond to the hydrogen. The bond between hydrogen and chlorine breaks. This gives us our secondary carbocation, which is not very stable. Since there is no hydrogen on the more substituted carbon adjacent, only a methyl could be shifted. We cannot shift anything larger than a methyl group. So a methyl group with its bonding electrons shifts over to the secondary carbocation. That would give the tertiary carbocation. The secondary carbocation would add chlorine to form the minor product at the secondary carbon. The tertiary carbocation adds chlorine at the tertiary carbon to form the major product. For identifying positions that can have a more substituted carbocation, you're going to look for a vinyl carbon that is next to a tertiary or quaternary carbon. Okay, so we have a vinyl carbon that is next to a tertiary carbon for our first example. In this case, the first cation formed is secondary. It shifts to this tertiary cation. Here we have a vinylic carbon next to a quaternary carbon. This is a carbon that has 4 bonds to carbon. 1, 2, 3, 4. Quaternary carbon. This one will perform a methyl shift. So a methyl group moves over to the secondary carbocation, resulting in the tertiary carbocation. More examples. Here we have a vinylic carbon that is already positioned at a tertiary carbon. The adjacent carbon is only secondary. The first carbocation formed is a tertiary carbon. In this case, the more substituted carbon is already present, a tertiary carbocation. There will be no shift. We have another example of a vinyl carbon next to a quaternary carbon. In this case, a methyl will shift to the secondary carbocation position, and we will form a tertiary carbocation. In our examples, only A, B, and D have rearranged. Let's look at E. E has a pi bond on a molecule that has only primary and secondary carbons. The first carbocation form is a secondary carbocation. So we can either form a secondary carbocation by this vinylic carbon adding hydrogen or by the other vinylic carbon adding hydrogen. There are no more substituted carbons next to the positive charge. Therefore, no shift will occur. So the carbocation does not rearrange if no improvement is possible. For example, the secondary carbocation formed here can only become, if a shift occurred, it would still be a secondary carbocation. So that is not possible. Also, you can note that it's not possible by counting 1, 2, and if the carbon that you count as carbon 2 is not more substituted, then no rearrangement will occur. We're going to move on to looking at our next reaction. BH3, borane, is an electrophile. BH3 is called borane, and borane is an electrophile. It is an electrophile because it is an incomplete octet. And remember, we defined our electrophiles as a positive charge, a partial positive charge, or an incomplete octet. Borane is an incomplete octet, and methyl cation is a positive charge and an incomplete octet. This reaction is called hydroboration-oxidation. This is another reaction in your functional group notebook. This reaction is number 6 in your functional group notebook, hydration of alkenes by hydroboration. You will need to memorize the reagents required to perform this reaction. This reaction will start with the reactant of an alkene and use the following reagents. First, in step 1, we'll use borane and THF. THF is an ether. It's called tetrahydrofuran. It's a cyclic ether, and it is simply the solvent. It does not have any purpose other than to perform a duty of solvation. This reaction will have the unique product, the only product in this chapter that forms through anti-Markovnikov addition, which means that the higher priority new functional group, hydroxyl group versus hydrogen, hydroxyl is higher priority, bonds to the carbon that has fewer bonds to carbon. And the lower priority group, hydrogen, bonds to the carbon that has more bonds to carbon. This reaction does not go through a carbocation intermediate, and so rearrangements will never occur. After our first step with borane and THF, the solvent, we will add hydroxide ion, peroxide, and water to finish off the reaction. I will go through the mechanism for this reaction. The electrophile is going to add to the sp2 carbon bonded to the most hydrogens, because this is an anti-Markovnikov reaction. So that is the difference between acid-catalyzed hydration and hydroboration-oxidation. One forms an alcohol group on a more substituted carbon, the other places the alcohol group on the less substituted carbon. The mechanism for hydroboration. In hydroboration, the first step 1 of the reaction where we have borane and THF, will add H and BH2 through a syn addition at the same time to the pi bond. What it means to add syn is that they both add on the same side of the pi bond. It would be like saying the molecule is cis. The H and the BH2 add to the same side. Hydrogen adds to the more substituted carbon, and borane adds to the less substituted carbon. But in this case, hydrogen is the nucleophile and borane is the electrophile. So the pi electrons bond to borane, and then hydrogen and its electrons bond to the more substituted carbon. This occurs relatively simultaneously, so that our products are H and BH2 on a solid wedge, or H and BH2 both on a dashed wedge. The added groups must add on the same bond type, both wedges or both dashes. And that is the end of 1. After we have gone through this first step of the reaction, this part, step 1, that is what the product is, the alkyl borane. When the sp2 carbon adds the electrophile boron to the carbon with the most hydrogens, this puts a partial positive charge on a more substituted carbon, so that we form a more stable transition state with a positive charge on a more substituted carbon when borane adds to the carbon with the most hydrogens. This reaction is, when we use BH3, very interesting because BH3 has a total of 3 hydrogens at the beginning of the reaction. Because it has the total of 3 hydrogens at the beginning of the reaction, borane will actually add one of our alkene starting materials for every 1 hydrogen bonded to boron, until we have a tri-substituted alkyl borane as our product. This all occurs before we move into reaction part 2. So after we form our first step of the alkyl borane that we showed, we add a second molecule of propene. Now we have a di-substituted alkyl borane. Then a third molecule of alkyl borane replaces the last hydrogen, giving a tri-alkyl borane. All of that is the first step of the mechanism for the first step of the reaction. This step. We still have to go through the second step of the reaction's mechanism. If instead we were to use a borane that already had 2 R groups, then instead of a 3 alkene to 1 borane ratio, if we already have a substituted borane to begin with, and only 1 hydrogen exists on our borane, then we would have a 1-to-1 borane to alkene ratio. Okay, so we're going to take our trialkyl borane and move on to step 2 of the reaction. In step 2 of the reaction, we have an oxidation reaction. And a hydroxyl group is going to replace our Br2 group. So we add hydroxide peroxide in water, and that results in hydroxyl group replacing Br2. This is an oxidation reaction because the number of carbon to oxygen bonds increases. So let's look at this mechanism from the beginning. We have 1 butene here as our example reacting with borane, showing arrows that the pi electrons bond to boron and the electrons that bonded hydrogen to boron then bond to C2 of the butene. So we've added BH2 and hydrogen across carbons 1 and 2. Then a second molecule of the propene will react with boron. The hydrogen will be moved on to carbon 2 of the alkene. The boron bonds at carbon 1 of the alkene. Now we have a disubstituted alkyl borane. Next step of the mechanism, the last B to H bond is replaced with the alkene. So C1 of another alkene bonds to boron, and the BH hydrogen bonds to C2 of the alkene. That gives us our trialkyl borane. On the next step, our trialkyl borane will react with hydroxide ion. The hydroxide ion will bond to boron, which is electrophilic because it has less than an octet. I'm sorry, this is the peroxide ion, not the hydroxide ion. So our peroxide ion bonds to boron. On the next step, one of the alkyl groups, one of the B to C bonds will break. The entire alkyl group will shift with its bonding electrons to the oxygen. That gives us back to a boron molecule that has only three bonds, a boron atom with only 3 bonds that is electrophilic because of an incomplete octet. And when the new C to O bond forms between the R group and the oxygen, a hydroxyl group will break off because oxygen should not have more than an octet. So when we form a new bond, another bond has to break. So this hydroxyl group breaks off, but in the next step, boron having less than an octet, the hydroxide ion bonds to the boron. And that gives us R2BOH. Boron, it has, in this case, a negative charge because it has more than an octet, or it has an octet. When boron has an octet, it has a negative charge. To form a more stable intermediate, the boron to oxygen bond of our alkyl group breaks. This forms an alkoxide ion. The boron to oxygen bond breaks for the alkyl group. The alkoxide ion will then pick up a hydrogen from the water molecules in solution. This will produce an alcohol and hydroxide ion. This will happen until all of the R groups of boron have been replaced by hydroxide ion, so that the final product is BOH3 plus 3 alcohol products. So you can see that this reaction will be very long because the reaction will continue until boron no longer has any alkyl groups. The mechanism of this reaction will probably not be asked about on an exam, other than to know where the OH binds versus the hydrogen, where the hydrogen binds, and in what way they bind, that they bind syn. So that when you see an alkene with the boron reagent, you should add a OH group to the less substituted carbon and a hydrogen to the more substituted carbon. But only when we have a boron present. Okay, so now we have halogenation of alkenes. I believe this is number 2 on your functional group notebook list.